We are going for the next topic here, hardness of water. What do I mean by hardness of water? Water can be classified as soft water as well as hard water. Soft water contains very less percentage of dissolved salts in it. Remember, when I say salt, I am not including sodium chloride into it. Sodium chloride is a common salt here. No. Whenever I mention the hardness of water, it is about the salts that is made by magnesium and calcium. These are the two cations which are incorporating the hardness in water. So basically, I classify this hard water into two types: temporary hardness and permanent hardness. For example, your mother is buying some detergent. She is trying to wash the cloths. She sees very good foam is formed. The cloths are becoming brighter. 2 streets behind, and another woman is buying the same rinse or same detergent, and she is also trying to wash her clothes. She is unable to find such kind of a foam formation here. So the question is not about the detergent that we use. Any detergent that you use, Rin, Surf Excel, Ariel, whatever it is, the chemical composition present in the soap is the same. There is no difference at all. So what is the real thing that has given the difference here? Very neighborhood, someone is getting good foam, the another one is not getting foam. The reason is water. If the water is a soft water, that means it is containing less percentage of dissolved salts in it, then foam formation will happen. Foam formation will happen. See, I am talking about soaps and I am treating with water. If this water is containing calcium or magnesium salt, we know what are soaps actually. They are sodium or potassium salts of fatty acids, isn't it?
Yes, ma'am.
So this calcium replaces the sodium or potassium to form white, dirty white turbidity or precipitate, which is called as scum. You could also witness this in a very during the prime summer times when Chennai goes dry. When you try to take bath, you could see it's not foaming. Instead, it is giving you some dirty white kind of a precipitate kind of a thing you will be getting from your body when you start doing this on your skin. This is nothing but due to the formation of scum on your skin here. So we are discussing about such a hard water. Two types of hardness are there: temporary hardness and permanent hardness. Temporary hardness are made or induced by the carbonates and bicarbonate salts of calcium and magnesium. I say CaCO3 is there, MgCO3 is there, right? Calcium bicarbonate is there, or magnesium bicarbonate is there. These will form temporary hardness. The permanent hardness will be made by the anions of chlorides and sulfates: calcium chloride, magnesium chloride, calcium sulfate and magnesium sulfate. Why do I differentiate it as permanent hardness and temporary hardness? The word itself is suggesting. For example, when let us take during your grandma's or grandpa's time, if they were in village places, when they want to boil the water, they could have taken a very big vessel, they would have filled water into it, and they put it on a gas stove or they put it on the fires to boil it. When they are using this same vessel for continuous period of time, let us say they are using nearly for 10 years or 11 years, something like that, you could see the inner walls of the container is having a thick whitish layer. Even at your home, if your mom is having this habit of boiling the water in the utensil in the same vessel for the continuous time, you could see there is some white deposition in the inner walls of the container. This is because that water that she was boiling was containing temporary hardness there. Just by boiling itself, let me say calcium carbonate is there. Just by boiling, it became CaO and CO2. The CO2 evolved from the container. It is a gas, it released. What about calcium oxide? It is a salt. It gets deposited on the inner walls of the container. Just because I am able to remove this hardness just by boiling, we call this as temporary hardness. The second type, the permanent hardness, cannot be resolved like this in a very simple manner. You need chemical processing here, like zeolite process or ion exchange resins. These process you need for treating the permanent hard water.
Okay, ma'am.
Okay. So what is the relatability that you are studying here right now? Because it is also one of the concentration term here. We are going to include. This hardness of water once upon a time was expressed in different units, French and Clark. Today, very uniformly we use the terminology ppm. ppm stands for parts per million. A million is 10 power 6, right? So how many parts you are having with respect to this 10 power 6 is given as parts per million. In other words, we say it's 10 power minus 6. Anything into 10 power minus 6. So we basically say, when I say it is 1 ppm, I am talking with respect to milligram per liter quantity, or I am saying it in gram per 10 power 6 ml quantity. Three ways of understanding it. Milligram by 10 power 3 ml. 1 ml is 10 power minus 3 liter, isn't it? So this would get cancelled. I get milligram per liter itself again. Correct?
Yes,
I
ma'am.
say this with respect to gram. 1 milligram is 10 power minus 3 gram. So can I write it as 1 divided by 10 power 3 into 10 power 3? Which is nothing but 10 power 6. So can I say it is gram by 10 power 6 ml?
Yes, ma'am.
This parts per million is always expressed in terms of equivalence of calcium carbonate. Though there are many salts here, we usually express this hardness only with respect to calcium carbonate here. Why? Why should I express only with terms of calcium carbonate? Because calcium carbonate is the most insoluble salt we have. Most sparingly soluble salt it is. First one. Second one, for calculation purpose, the molecular weight of calcium carbonate is 100 gram. The equivalent weight is 50 gram. It is easy for me to use such a kind of a numbers when you do calculation. So these are the two reasons why we always express the hardness in terms of ppm equivalents of calcium carbonate.
Okay, ma'am.
So let us start here. We assume that whatever is the parts per your milligram or your ppm quantity of CaCO3, that will be equivalent to the consecutive salt here. We will see it with an example. A sample of water is having 111 milligram per liter of calcium chloride in it. We express the hardness in ppm equivalents of calcium carbonate. So step number 1, equivalent weight of the respective salt is equal to equivalent weight of calcium carbonate. This is the equivalence always. What is the equivalent weight of calcium carbonate, Lakshana?
50 gram.
50 gram, very good. So I say 50 grams of calcium carbonate will be equivalent to the equivalent weight of calcium chloride here. Okay. The molecular weight of calcium chloride is 111. Then what will be its equivalent weight?
Triple 1/2, ma'am.
Triple 1/2, correct, because it is a salt. Whatever is the charge, that will be the n factor here. So it's triple 1/2, which is 55.5 grams is the equivalent weight for us. Okay, wow. So 55.5 grams of CaCl2 is nothing but equal to 50 grams of CO3. How much is provided here? Triple 1 milligram. Then how much will it be? The double of it?
Yes, ma'am.
Correct, Lakshana, do you understand this?
Yes, ma'am.
55.5 is equivalent to 50. Here I am doubling it. Then here also I should have doubled it. Correct, Appa? So what you are writing is 100 milligram per liter of calcium carbonate. What is milligram per liter? ppm. So can I say it is 100 ppm of CaCO3?
Yes, ma'am.
Yes, ma'am.
Let's look at this question. Water is containing 36 milligrams of MgSO4 per kg of water. Okay, so per kg, we know density of water is 1. So when I say 1 kg of water, does it mean 1 liter of water?
Yes, ma'am.
So it is nothing but 36 milligram per liter of magnesium sulfate is available. They are asking you to express degree of hardness here. What did I say? Equivalent weight of the salt should be equal to equivalent weight of calcium carbonate. Understood? The molecular weight of magnesium sulfate is 120. What is the n factor?
2.
2. So what will be the equivalent weight? 60 then. So I say 60 milligram per liter of MgSO4 is equal to 50 mg per liter of CaCO3. How much is provided to you? 36 mg per liter. Calculate how much mg per liter of calcium carbonate it is. So I have got it is 30 mg per liter, which is nothing but 30 ppm.
Done, ma'am.
Okay. Now we are doing the experimental method of identifying the hardness of the water or determining the hardness of the water. To this, I am doing a titration here where I am using odd water. That means, ma'am, I am taking a conical flask. I am filling it with tap water. So any tap water will definitely contain calcium and magnesium salts. I am taking a burette. In the burette, I am filling with a reagent called as EDTA. EDTA is nothing but ethylene diamine tetraacetic acid. Ethylene diamine tetraacetic acid, EDTA. Let's look at the structure of EDTA here. Ethylene means ethyl molecule from which the compound has got originated. Ethyl contains 2 carbon. Look at this. Initially CH3, isn't it? This is ethane. To this diamine is attached. Amine means NH2 group. So to this, one of the hydrogen I am removing from here. 2 hydrogens are there, which is connected. Each is connected with 1 nitrogen. How many hydrogen the hydrogen is having? How many nitrogen has? 2 hydrogen.
2, ma'am.
This has 1, 2. This is also having 1 and 2. Go for the next name. Tetraacetic acid. What is acetic acid? CH3COOH. Correct. I said tetra. That means how many are there? 4 are there. So remove each hydrogen from here and block it with this acetic acid. Acetic acid is CH3, right? I am bonding here, so it has to be CH2 COOH. Similarly this side CH2 COOH. Similarly this side CH2 COOH. CH2 COOH. This is EDTA. Ethylene diamine tetraacetic acid. Okay, why did you use EDTA here? This titration is called as complexometric titration. This titration is called as complexometric titration, where you create a complex here. I am already having here calcium is there, magnesium is there. I am trying to trap this metal ion using some kind of a captivating agent, just like a magnet. Okay, so this EDTA is called as a ligand. In 12th we will be learning about this. Ligands are electron rich sources. It's having so much of electron here. Ma'am, where it is having electron? Look at this nitrogen. Nitrogen brings 5 electron for the bonding. But here nitrogen is making only 3 bonds. So this nitrogen and this nitrogen is having lone pair of electron. Not just that. This is an acid. They can release H plus here. So that I am having 4 negative charges. Can you see this?
Yes, ma'am.
When COOH is releasing H plus, what is the other ion that you create? Carboxylate ion. COO minus. Now count the negatives that you have got here. 1, 2, 3, 4, 5, 6. 6 electron density you have created. So only I call it hexa. Hexadentate ligand. Dentasy means how many places it can go for bonding. Here I am having 6 spots in which the bonding can happen. These 2 nitrogen can also come and cover up the calcium. All these 4 acids also can come and cover up the calcium and magnesium here. So I am calling it as hexadentate ligand. So I took it the EDTA in the burette. I have taken the salt solution in the conical flask. To this I am adding EBT indicator. Just like a phenolphthalein or methyl orange, I am adding EBT indicator. Initially, before I am adding EDTA, ma'am, I am having a conical flask. I have filled it with hot water. To this I added EBT indicator. EBT is nothing but areochrome black tea. The name of the indicator is areochrome black tea. Adding this, along with that, I am going to add a buffer solution. The buffer solution is ammonia and ammonium chloride buffer solution. NH3, NH4Cl. Together, this solution is called as buffer solution. Why should I use a buffer? I don't want to see a dramatic change in the pH. I want to maintain the pH at 9 to 11 itself. So a buffer is added. You can see I am adding a weak base and its salt. Ammonia is a weak base and its salt. Can you see it is ammonium chloride here? Weak base and its salt I am adding. It is a buffer. So the moment I added it without EDTA, the color of the solution is wine red in color. Once I started adding EDTA to it, initially the calcium and magnesium, Ca2 plus and magnesium 2 plus would have got attracted by EBT. So they are having a very weak interactive force between them. The moment this gigantic EDTA comes from the burette and falls into the conical flask, Calcium, magnesium says EBT, you are having very less amount of electron, we don't like you. Instead, EDTA is serving me so many donor sites. So many donations are there from EDTA. So let me go and bond with it. So you can see calcium EDTA complex and magnesium EDTA complex is formed. So that EBT is becoming free. As the EBT comes out free, it turns into steel blue in color. This is the end point of this titration, from wine red to steel blue. Okay. Now, how do we proceed with this reaction, ma'am? So basically, you will be provided a solution at first where they say it's standard odd water. That means they know exactly how much calcium and magnesium is there. They titrate with this EDTA to find the concentration of the EDTA. Once it is done, they will take this water, they will be giving you another water which is nothing but the boiled solution of the first water. Let me say they took 100 ml, they gave 50 ml as a first solution, another 50 ml after boiling it. Boiling means don't assume that the volume has got decreased. Slowly they gently heated it so that carbon dioxide left the place. Okay, now this is hot water. In this hot water, which hardness will be there? Temporary or permanent?
Temporary.
Temporary, ma'am.
Think and say. You boiled it. Don't you think when you boil it, temporary hardness will leave?
Yes, ma'am.
So which hardness you will have?
Hardness, ma'am.
Permanent hardness. Now you titrate, you will be able to calculate how many permanent hardness is present. When you subtract the initial minus the permanent, you will get temporary hardness value. Okay, let's see a question here so that you understand. One ml of EDTA is equal to 1.8 milligrams of calcium carbonate. 1 ml of EDTA is equal to 1.8 mg of calcium carbonate. What do I mean by that? Every 1 ml of EDTA is containing how much milligrams, how much type of hardness here, because what is the work of EDTA? It is going to go and captivate the calcium ions. So every 1 ml of EDTA that has got consumed tells you the water is having every 1 ml corresponds to 1.8 milligrams of calcium carbonate that is present in water. If 50 ml of hot water needs 30 ml of EDTA, express the degree of hardness. You know very well, hardness will be expressed in terms of ppm of calcium carbonate, correct? So they are giving a standard value. This value is called a standard value. 1 ml of EDTA is equal to 1.8 mg of CaCO3. Clear? So I have to calculate how much is calcium carbonate available in the water, isn't it?
Ma'am.
Saying, tell me, Pa.
Is the standard like 1 ml is always equal to 1.8 mg of CaCO3?
Louder, be louder.
Is it standard or can it change?
Standard value for this titration. Every
Okay,
titration they will be providing you another value. Okay. They are telling you if 50 ml of hot water, I am adding 50 ml of hot water and it required 30 ml of EDTA. How much is the degree of hardness? I just got to know 1 ml of EDTA is equal to 1.8 mg of CaCO3. Then what about 30 ml of EDTA? 1.8 into 30 mg of CaCO3, correct?
Yes, ma'am.
So this much mg of CaCO3 is present in how many ml of water? 50 ml of water, correct? Children?
Yes, ma'am.
1 ml of EDTA is 1.8 mg CaCO3. I am calculating for 30 ml of EDTA here. how much is the CaCO3 here, okay? But I needed to express it in ppm quantity. What is ppm? Milligram per liter.
Yes, ma'am.
So this is for 50 ml. I am calculating for 1 liter here. That's it. How much you are calculated is for 50 ml, but I need it for 1 liter. That means for 1000 ml. How much is that? That gives you the ppm quantity of CaCO3.
Into 20, ma'am.
That's it. Understood, both of you?
Yes, ma'am.
I thought I can complete the missed out session of Monday today, but I am unable to complete it today.